हेलो गुड मॉर्निंग एवरीवन। आज हम लोग आइडेंटिटी थ्योरम पढ़ने जा रहे हैं। आइडेंटिटी थ्योरम ऑफ फर्स्ट फॉर्म। लेट f is a continuous function on R and S is a subset of R such that S dash is equal to R. That means S is dense in R. Example of dense sets is S is equal to Q, set of all rational number dense in R, set of all irrational number dense in R, set of all algebraic number dense in R, set of all transcendental number dense in R. S alpha equal to m plus n alpha such that mn belongs to Z and alpha belongs to set of all irrational number is also dense in R. And a statement of identity theorem is f is continuous function on R and S is a subset of R such that S dash is equal to R, and if for all x belongs to S fx equal to 0 then fx is identically 0, then fx is identically 0 for all x belongs to S. अब हम लोग प्रूफ देखते हैं। प्रूफ और थ्योरम के प्रूफ से हम लोग को बहुत चीज सीखने को मिलेगा, हाउ टू थिंक एंड हाउ टू सॉल्व द प्रॉब्लम। ओके, since S dash is equal to 1, that means any elements of R you can, if you choose any elements of R, then there exists a sequence in S which converges to alpha. Let alpha belongs to R, then there exists a sequence an which converges to alpha as n tending to infinity. Why? Because S dash is equal to R, that means every point of R is a limit point of S. Then any elements of R you can construct a sequence which converges to alpha. That means there exists a sequence which converges to alpha as n tending to alpha. And also given that in a statement of identity theorem, f is continuous on R. If f is continuous on R, since f is continuous on R, by definition of continuity, we can say that sequence f an converges to f of alpha, where by definition of continuity, by definition of sequential definition of continuity. Okay, since an belongs to S minus alpha implies f of n equal to 0 for all n belongs to natural number, which is given in the statement. C statement. If x belongs to S, then fx equal to 0. If x belongs to X, then fx equal to 0. Then we have to show that fx is identically 0 for all x belongs to R. Since an belongs to S minus alpha, that's why implies f of an equal to 0 for all x belongs to natural number, for all n belongs to natural number. That means sequence f of an converges to 0, which is equal to f of alpha. Since alpha is an arbitrary element of real number, alpha is an arbitrary element of R. That's why, therefore, fx equal to 0 for all x belongs to real number. hence proved. Now see one note. Okay, note, let f is a function on the closed interval 0, 1 to r be a continuous function. And s is equal to closed interval 0, 1 intersection q. Then s dash is equal to closed interval 0, 1. We have implies fx equal to no. If fx equal to 0 for all x belongs to x, then implies fx equal to fx identically equal to 0 for all x belongs to closed interval 0, 1. Okay, now see the proof. Since s dash is equal to 0, 1, let alpha belongs to 0, 1, then there exists a sequence an which converges to a alpha as n tending to infinity. Also given that f is continuous. F is continuous on closed interval 0, 1. By definition of continuity, we can say that sequence f of an converges to 0 as n tending to infinity by definition of continuity. Which is equal to f of alpha, that since alpha is an arbitrary element of closed interval 0, 1, therefore f of alpha equal to 0 for all alpha belongs to closed interval 0, 1. That means fx equal to 0 for all x belongs to closed interval 0, 1. Now see the second form of identity theorem. Second form of identity theorem. Let f, g is a function from R to R. Be a continuous function. And S is a subset of R such that S dash is equal to R. If fx equal to gx for all x belongs to S, then fx identically equal to gx for all x belongs to R. Proof. Since S dash is equal to R and fx is equal to gx for all x belongs to R, and f and g are continuous function on R, if we let hx equal to fx minus gx, then fx and gx also continuous function. Let hx equal to fx minus gx, then hx equal to 0 for all x belongs to S. Since S dash is equal to R, let alpha belongs to real number, implies there exists a sequence, n which converges to alpha as n tending to infinity. An belongs to S minus alpha. N belongs to S minus alpha. Since f is continuous and g is continuous, that's why h is continuous. Hx is continuous on R. By definition of continuity, sequence f of h of an converges to h of alpha as n tending to infinity. Since an belongs to S minus alpha, implies h of an equal to 0. Implies sequence h of an converges to 0, which is equal to h of alpha. That means since alpha is an arbitrary element of set of all real number, that's why hx equal to 0 for all x belongs to R. That means identically equal to 0. Fx is equal to gx for all x belongs to real number. This is the second form of identity theorem. Okay. In this class we study first form of identity theorem. A statement of first form of identity theorem is f is continuous on R and S is subsets of R such that S dash is equal to R. And if for all x belongs to S, fx equal to 0, then fx is identically 0. And हम लोग नोट में देखे थे कि f is continuous function on closed interval 0, 1 and S is equal to closed interval 0, 1 intersection q such that such that S dash is equal to close interval 0, 1. Actually this is implies, okay. If S is equal to close interval 0, 1 intersection q, then implies S dash is equal to close interval 0, 1. If fx is equal to 0 for all x belongs to S, then fx is identically 0 for all x belongs to close interval 0, 1. एंड हम लोग उसके बाद सेकेंड फॉर्म ऑफ आइडेंटिटी थ्योरम देखे थे. सेकेंड फॉर्म ऑफ आइडेंटिटी थ्योरम इज let f and g is continuous function on R and S is subsets of R such that S dash is equal to R. If fx equal to gx for all x belongs to S, then fx equal to gx for all x belongs to real number. Okay, thank you. Bye bye.